What if one of the biggest ideas in modern cosmology is completely wrong? Dark energy is supposed to explain why the universe is expanding faster and faster, but what if everything we think we know about it doesn't hold up anymore? New observations, unexpected data, and bold theories are starting to challenge the foundations of our understanding of the cosmos. In this video, we'll explore why scientists are questioning dark energy and what it could mean for the fate of the universe itself. Before we dive in, make sure to like this video if you enjoy mind-bending science, subscribe to Noah Science for more deep explorations of the universe, and share this with anyone who loves space and big questions. Thank you so much for watching and supporting the channel. Now let's begin. In the distant future that current cosmology describes, the universe drifts toward an almost featureless state. Galaxies slip farther apart, their light stretched until it fades into wavelengths that no existing instrument could hope to detect. Stars run out of fuel, cool, and end as dark remnants. Even black holes, the most persistent structures known, slowly leak away their mass through a slow quantum process until they vanish. What remains is a thin wash of particles and radiation spread across an ever larger volume of space, with temperature hovering just above absolute zero. This scenario is known as the Big Freeze, and for many years it has stood as the dominant scientific picture of how cosmic history ultimately concludes. It is not a dramatic ending. There is no final explosion or instant of collapse, only an extended decline in activity as the universe continues to expand and to dilute everything it contains. It is a future that follows directly from the numbers that describe the universe today, from the way galaxies move from the pattern of the oldest light, and from the presence of an unseen influence called dark energy that appears to be driving an accelerated expansion of space itself. Modern cosmology rests on a framework that connects these observations into a single story. In this story, almost all of the energy in the universe resides in forms that cannot be seen directly. Ordinary matter, the kind that makes up stars, planets, gas dust, and living organisms, contributes only a small fraction of the total. A larger share is in dark matter, a substance that does not emit or absorb light, but reveals its presence through gravity shaping galactic rotation curves and the large-scale web of galaxy clusters. The largest share belongs to dark energy, which behaves as a property of space rather than as a conventional material component. When cosmologists speak in terms of proportions, they find that roughly 2/3 of the cosmic energy budget appears to be dark energy, a little more than 1/4 appears to be dark matter, and only a few percent is ordinary matter and radiation. These ratios are inferred from independent measurements from the pattern of temperature variations in the cosmic microwave background, which is the faint afterglow of the early universe, from the way galaxies cluster on large scales, and from the relationship between distance and redshift for particular astronomical objects used as standard candles and standard rulers. Taken together, these lines of evidence point to a universe whose expansion is not slowing but accelerating under the influence of this dark component. In the widely used model that ties these facts together, dark energy is treated as a constant feature of the cosmos. This constant is often traced back to a term that Albert Einstein once introduced into his equations of general relativity to allow for a static universe, and later abandoned. In the modern version, it reappears as a simple way to account for an energy associated with empty space itself. If dark energy is truly constant in time and uniform in space, the equations that describe the evolution of the universe become relatively straightforward. The expansion rate decreases from its early violent state after the Big Bang, but because dark energy does not dilute as the universe grows larger, in the same way that matter and radiation do, its influence eventually dominates. Once that happens, the expansion of space accelerates and continues to accelerate, and any hope that gravity might bring the expansion to a halt or reverse, it disappears. Under this assumption, the Big Freeze is not just a possibility, but an almost unavoidable outcome. The cosmic future appears to be locked in by a parameter that is built into the current standard model of cosmology. For a long time, this picture has been attractive because of its simplicity and because it matches a wide variety of measurements with impressive precision. Astronomers can take this model, adjust a small set of parameters, and reproduce the observed distribution of galaxies, the details of the cosmic microwave background, and the brightness of distant supernovae. Space agencies such as NASA and the European Space Agency have planned missions and interpreted data using this framework, finding that it consistently explains what they observe on scales ranging from the solar neighborhood to the most distant quasars. This success, however, carries a subtle cost. The more the model appears to work, the more it encourages the belief that the underlying assumptions are correct, including the assumption that dark energy is constant and featureless. Yet those assumptions cannot be measured directly. The universe offers only finite volumes, finite times, and finite observational tools, and within those limits, cosmologists infer the properties of an entity that neither emits light nor interacts with matter in any conventional way. When that entity is assigned almost 2/3 of the total energy content of existence, even small uncertainties in its behavior can have large consequences for predictions about the future. This consensus becomes less secure when different ways of measuring the expansion of the universe do not quite agree. Some methods grounded in the early universe and the cosmic microwave background suggest one value for the current expansion rate. Other methods based on the distances to nearby and intermediate galaxies suggest another. The tension between these values is not enormous, but it is persistent, and it has grown as data have improved. At the same time, increasingly detailed surveys of galaxies and clusters map the cosmic web with finer resolution, sometimes revealing subtle mismatches between observation and model. None of these discrepancies alone is enough to overturn the standard picture, but together they hint that the simple assumption of a perfectly constant dark energy may be hiding a more complex reality. If dark energy has changed over cosmic time even slightly, then the ultimate fate of the universe is not as fixed as current textbooks suggest. In that case, the Big Freeze would no longer be the unique, inevitable horizon, but only one of several possible futures that depend on properties of the universe that are just now coming into reach of precise measurement. In the late 20th century, the path that leads to dark energy begins with a simpler question: how fast is the universe expanding, and how has that speed changed over time? For much of the century, astronomers assume that gravity, the attractive force between all forms of mass and energy, should act as a brake on expansion. In this view, the universe begins in a hot, dense state, expands rapidly, and then gradually slows as galaxies pull on one another. The task is to work out whether this slowdown is strong enough to halt expansion entirely in the distant future, or whether the universe will continue to grow forever, but at an ever-decreasing rate. The central quantity that links these possibilities is the expansion rate today, often summarized in a single number known as the Hubble constant. This number describes how quickly distant galaxies recede as a function of their distance. To measure it directly, astronomers need two things: accurate distances to faraway galaxies and precise measurements of how quickly those galaxies are moving away, inferred from the redshift of their light. Redshift occurs when light stretches to longer wavelengths as space itself expands between its source and its observer. The deeper the redshift, the greater the apparent recession speed, and the farther back in time the light was emitted. For nearby galaxies, astronomers have long used certain kinds of stars as distance markers. In particular, Cepheid variable stars, which pulse in brightness with a period that relates closely to their true luminosity, have served as reliable standard candles. By comparing how bright such a star appears to how bright it is known to be, the distance to its host galaxy can be calculated. However, Cepheid stars are relatively rare and not bright enough to be seen clearly at the great distances needed to trace the expansion history over billions of years. For this purpose, a different kind of cosmic marker proves more useful, type 1, a supernovae. These are thermonuclear explosions of white dwarf stars in binary systems, where a white dwarf accumulates material from a companion until it reaches a critical mass and ignites in a runaway reaction. The resulting explosion outshines an entire galaxy for a short time and reaches a peak luminosity that is remarkably uniform from one event to another. This near uniformity allows type 1 a supernovae to serve as powerful standard candles on cosmological scales. In the 1990s, two major teams set out to use these supernovae to refine measurements of the expansion rate and its change over time. They gathered data on dozens of distant supernovae, carefully measuring their light curves, which describe how brightness rises and falls, and their redshifts, which indicate how much the universe has expanded since the light was emitted. The expectation is straightforward. If gravity has been slowing the expansion, then very distant supernovae, whose light left them when the universe was younger, should appear slightly brighter than they would in a universe that has always expanded at the current rate. Their light would have had to travel through a cosmos that was expanding more slowly, and thus they would be closer than they would be in a model with constant expansion. Instead, the observations reveal the opposite. The distant type 1, a supernovae, appear fainter than they should under a decelerating or even constant expansion. The best way to reconcile their faintness with their redshifts is to conclude that the universe has been expanding faster in recent times than it was when the light began its journey. In other words, the expansion is accelerating. This conclusion is not reached lightly. The team scrutinized their data, searching for sources of error. They examined the possibility that distant supernovae might be intrinsically different from nearby ones, that dust might be dimming the light more than expected, or that selection effects might bias the sample. They adjust their models to account for these factors, and still the signal persists. Supernovae at high redshift are systematically too faint. The implication that follows is profound. Somewhere in the equations that describe the universe, an additional component is required, one that exerts a repulsive influence on cosmic scales. It cannot be ordinary matter, because matter attracts through gravity and would only slow expansion. It does not behave like radiation, which also contributes to gravitational attraction. Instead, it behaves like a smooth energy associated with space itself, with a pressure that drives expansion faster rather than slower. Cosmologists adopt the term dark energy for this unknown component, partly to acknowledge its mysterious nature and partly to distinguish it from dark matter, which acts through gravity in the conventional way. The effect of dark energy is easiest to picture, not by imagining a force pushing on galaxies in the usual sense, but by recognizing that the fabric of space is itself changing in such a way that distances between unbound objects grow at an increasing rate. In this picture, galaxies do not fly through space as much as they are carried apart as space stretches. The recognition that expansion is accelerating forces a reworking of cosmological models. When the contributions of ordinary matter-dark matter radiation and this new dark energy are combined within the framework of general relativity, a consistent picture emerges that matches the supernova data and other observations. The new models show a universe in which dark energy overtakes matter as the dominant influence on cosmic evolution after several billion years, and in which acceleration becomes the defining feature of late-time expansion. This shift also transforms how scientists think about the fate of the universe. If dark energy maintains a constant density as the universe expands, it will continue to dominate more and more as matter becomes ever more diluted. The long-term outcome in such models is the big freeze described earlier, an endlessly accelerating expansion that thins out all structures over immense timescales. The discovery of acceleration through supernovae does more than alter the future. It raises questions about the past. Why did acceleration begin when it did? Why does the density of dark energy today appear to be of the same order of magnitude as the density of matter, even though they evolve differently as the universe expands? This apparent coincidence, sometimes called the cosmic coincidence problem, suggests that there may be deeper principles at work that are not yet understood. It also emphasizes how delicately balanced the cosmic inventory is. If dark energy had been much stronger in the past, galaxies might never have formed. If it had been much weaker, the universe might have recollapsed long ago. Instead, it sits in a range that allows complex structures and extended cosmic history. This balance prompts some researchers to wonder whether dark energy is truly a fixed property, or whether it might change in ways that are only now becoming observable as surveys push to greater depths and precision. In the years that follow the recognition of cosmic acceleration, cosmologists work to assemble a single coherent framework that can bring together many different observations under one roof. The result is a model often called the lambda cold dark matter model, which acts as the current standard description of the universe from its earliest moments to its distant future. In this framework, the symbol represented by the word lambda stands for the cosmological constant, a term in the equations of general relativity that behaves like a uniform energy associated with empty space. Cold dark matter refers to a form of matter that moves slowly compared with the speed of light and does not interact with radiation except through gravity. Ordinary or baryonic matter, which makes up stars, planets, and gas, appears as a relatively minor but still essential ingredient. Each of these components leaves a different imprint on the cosmos, and by studying those imprints, scientists can reconstruct the history of expansion and structure formation. One of the most important sources of information comes from the cosmic microwave background, a faint sea of microwave radiation that fills the sky. This radiation is a leftover from an early hot phase when the universe was dense and opaque, and it carries a detailed pattern of tiny temperature differences from place to place. Space-based missions such as the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite have measured this pattern with high precision. The statistical properties of these fluctuations, such as their typical size and distribution, depend sensitively on the total amount of matter, the proportion of dark matter to ordinary matter, and the presence of a cosmological constant or dark energy component. When the lambda cold dark matter model is applied to these data, it reproduces the observed pattern remarkably well, suggesting that the basic ingredients of the model are correctly chosen at least to first approximation. Another line of evidence comes from the large-scale distribution of galaxies. Over billions of years, small variations in the density of matter grew under the influence of gravity into the cosmic web seen today, with filaments of galaxies surrounding large voids and clusters forming at the intersections. Supercomputer simulations that start with tiny random fluctuations and evolve them forward under the laws of gravity and expansion produce patterns that look very similar to the observed galaxy distribution when they include cold dark matter and a cosmological constant in the proportions inferred from the cosmic microwave background. This agreement between simulation and observation reinforces the idea that dark matter and dark energy together shape the universe on the largest scales. On smaller scales within galaxies and clusters, dark matter reveals itself through the motions of stars and gas and through gravitational lensing, the bending of light by mass. Spiral galaxies rotate in such a way that their outer regions move faster than can be explained by the visible matter alone. Clusters of galaxies contain hot gas that would escape if only the gravity from visible galaxies were present. Gravitational lensing maps show that there is far more mass in these systems than the luminous components account for. These observations point to a dominant dark matter component that behaves like a pressureless fluid, clustering under gravity but otherwise remaining invisible. Dark energy, by contrast, does not clump on these scales. It appears as a smooth background influencing the overall expansion rate rather than the internal dynamics of galaxies. When all these strands are combined, a consistent picture emerges in which the universe is spatially close to flat on large scales, with its energy budget divided into three main parts. A little less than 3/4 appears as dark energy, a little more than 1/4 as dark matter, and only a small remainder as ordinary matter and radiation. In this picture, dark energy is characterized by an equation of state, a relation between its pressure and its energy density, that for a pure cosmological constant takes a specific fixed value. If this relation holds exactly, dark energy remains constant in time and does not vary from place to place. This simplicity makes the model powerful and predictive. Once a small set of parameters is chosen to match early universe data, the model automatically predicts the later behavior of galaxies clusters and supernova brightness as a function of redshift. Again and again, these predictions have matched observations within their uncertainties. The success of the lambda cold dark matter model leads many to refer to it as the standard model of cosmology, in analogy with the standard model of particle physics that describes fundamental particles and forces. However, the analogy is not perfect. In particle physics, the constituents of the standard model have been detected directly in laboratories and their properties measured in controlled experiments. In cosmology, dark matter and dark energy are inferred from their gravitational effects, and their microscopic nature remains unknown. No known particle in the existing catalog fits the role of dark matter, and dark energy might not even correspond to particles at all. It could instead be a property of the vacuum itself or a manifestation of an underlying field that has no direct counterpart in everyday experience. This situation creates an interesting tension. On the one hand, the model fits a wide range of astronomical observations with impressive quantitative accuracy. On the other hand, two of its three main components are not understood at a fundamental level. Dark matter candidates range from undiscovered particles to more exotic possibilities such as primordial black holes or other compact objects. But so far, dedicated searches have not confirmed any single explanation. Dark energy is even more elusive. Simple calculations of the vacuum energy from known quantum fields produce values that are many orders of magnitude, larger than the dark energy density inferred from cosmology, an enormous mismatch that suggests that some crucial piece of theoretical understanding is missing. Because of this, many researchers treat the lambda cold dark matter framework as an effective description, a model that works well over the range of scales and times that can currently be probed but might be replaced or extended once deeper physics is uncovered. Within this view, the assumption that dark energy is a strict constant is both a strength and a potential weakness. It is a strength because it yields a model that is mathematically simple and constrained. It is a weakness because it may limit the ability to recognize more subtle behavior if the data begin to point beyond the simplest case. If dark energy is not exactly constant but changes slowly over cosmic history, its effects could be small enough to have escaped detection in earlier, less precise surveys, while still being large enough to alter the ultimate fate of the universe. The search for such deviations motivates a new generation of experiments. Astronomers design surveys to map the expansion rate at different epochs with higher precision to trace the growth of structure over time and to compare the results with the predictions of the constant dark energy model. If even a slight drift is found in the effective strength of dark energy, it would signal that the cosmological constant is not the complete story. It would open the door to models in which dark energy behaves like a field that evolves, or in which the laws of gravity themselves change on the largest scales. The quiet elegance of the standard model of cosmology would then give way to a more complex and potentially more informative picture in which the universe is not governed by a single unchanging parameter, but by a component that has its own history. In that case, the long-term forecast of a simple big freeze would no longer be guaranteed, and the cosmic future would once again become an open question. In the early years after the acceptance of dark energy and the lambda cold dark matter framework, each new observation seems to strengthen the picture rather than weaken it. Space missions refine measurements of the cosmic microwave background ground-based telescopes, map galaxy distributions in larger and larger volumes, and supernova surveys extend distance measurements to greater redshifts. Within the uncertainties of those early datasets, everything appears broadly consistent. Over time, however, as instruments improve and statistical errors shrink, small but persistent differences begin to appear between the values of key parameters inferred by different methods. One of the most prominent of these differences involves the present-day expansion rate of the universe, the quantity often summarized as the Hubble constant. When this rate is inferred from observations of the very young universe, particularly from the pattern of fluctuations in the cosmic microwave background measured by satellites such as Planck, it takes one specific value within narrow error bars. When the same rate is inferred from observations of the relatively nearby universe through distance ladder techniques that use Cepheid variables and type 1 a supernovae, it consistently takes a higher value. Both methods are based on well-established physics, both have undergone extensive scrutiny, and both use independent data sets. Yet the gap between them remains and has grown more statistically significant with time. If the standard model is exactly correct, these determinations should converge as measurements become more precise. The fact that they do not is unsettling. Researchers invest considerable effort in searching for conventional explanations. They examine calibrations of distance indicators, reassess the handling of dust and intervening material, and refine models of the early universe used to interpret the cosmic microwave background. Some proposed resolutions involve systematic errors that may have been underestimated in one or both methods. Others invoke new physics, such as additional forms of radiation or changes in the behavior of dark energy at early times that would alter the relationship between early universe parameters and the later expansion history. For now, there is no consensus. The discrepancy does not yet prove that the standard cosmological framework is wrong, but it refuses to vanish as easily as many had expected. The expansion rate is not the only place where measured values seem to strain against the model. Another important aspect of cosmic evolution is the growth of structure, the way in which small early density fluctuations grow into the galaxies and clusters seen today. The rate at which structures grow depends on how much matter there is, how strongly gravity pulls, and how quickly the universe expands. Dark energy influences this growth indirectly by altering the expansion history. If dark energy is constant and behaves exactly like a cosmological constant, the relationship between expansion and structure formation follows a specific pattern. Large galaxy surveys and weak gravitational lensing studies provide direct ways to measure how clumpy the universe is on various scales at different times. Weak lensing refers to the subtle distortion of the shapes of distant galaxies by the gravitational influence of matter along the line of sight. By analyzing the statistical properties of these distortions across wide areas of the sky, scientists can infer the distribution and amount of matter, both dark and ordinary. Several surveys using different telescopes and analysis methods have reported measurements of the present-day clumpiness of matter that are somewhat lower than what the standard model predicts when normalized to the early universe data. This means that in these observations, structures seem to have grown slightly less than expected. As with the tension in the expansion rate, this difference is not enormous, but it is persistent across independent efforts. It could be due to subtle systematic effects in shape measurements, in the modeling of galaxy biases, or in the treatment of observational noise. It might also point to changes in the laws that govern gravity on large scales, or to properties of dark energy that differ from the simple constant case. In addition to these broad tensions, there are other smaller discrepancies scattered across cosmological data sets. Certain measurements of cluster abundances, which count the number of massive clusters of galaxies as a function of redshift, sometimes suggest slightly different parameter combinations than those preferred by the cosmic microwave background. Some analyses of baryon acoustic oscillations, which track a preferred scale in the distribution of galaxies imprinted by sound waves in the early universe, hint at minor shifts compared with model expectations when combined with other probes. None of these differences alone would justify declaring the standard framework broken. Observational cosmology is complex, and each step from raw data to final parameter values involves many choices and corrections. However, the pattern that emerges is one in which independent measurements taken at different epochs and using different techniques seem to be nudging the inferred parameters in directions that are not perfectly aligned. For a model that has only a handful of fundamental parameters, these nudges matter. If every observation pointed to the same combination of matter density, dark energy density, and dark energy behavior, the case for an unchanging cosmological constant would be extremely strong. The fact that some observations appear more comfortable with slightly different values leaves room for alternatives. One class of alternatives involves dark energy that is not strictly constant, but evolves slowly with time. In such models, often grouped under names such as dynamical dark energy, the effective pressure and density of the dark component change as the universe expands. The expansion history then deviates subtly from the constant case, especially at intermediate redshifts. This, in turn, can shift the inferred Hubble constant from early universe measurements and alter the predicted growth of structure. Another class of alternatives modifies the laws of gravity on large scales, allowing gravity to behave slightly differently over cosmological distances than it does in the solar system. These modified gravity scenarios are constrained by many observations and must be carefully crafted to avoid conflict with existing tests of general relativity, but they remain an active area of research motivated partly by the growing set of cosmological tensions. The community treats these possibilities with care. It is easy to overinterpret small discrepancies in complex data, especially when there is a strong desire to find signals of new physics. To guard against this, teams work to improve their analysis, pipelines to cross-check results with independent methods, and to design future surveys specifically aimed at testing whether these tensions are real or the products of unrecognized systematics. Yet, even with this caution, the mere existence of multiple coherent anomalies encourages a re-examination of the assumption that dark energy is a perfectly featureless cosmological constant. If the dominant component of the universe has its own dynamics, those dynamics would be subtle on human timescales but significant over billions of years. They would influence not only the interpretation of existing data, but also the forecast of the cosmic future. In such a context, the question naturally arises, has dark energy itself changed over the history of the universe? Until recently, answering that question with any precision has been difficult. Measuring slight variations in a component that is smooth and invisible requires large samples of tracers, wide and deep sky coverage, and careful combination of multiple observational probes. This is where modern large-scale surveys and specialized instruments become crucial. By mapping millions of galaxies, by tracking the pattern of baryon acoustic oscillations across cosmic time, and by combining these maps with supernova data and measurements of gravitational lensing, astronomers can begin to reconstruct how the influence of dark energy may have evolved. The first hints that something might be changing have emerged from such combinations, and they suggest that the picture of dark energy as a fixed background could be incomplete, or at least that this hypothesis is now finally being tested with the precision it demands. The standard model of cosmology remains an excellent, effective description, but it now occupies a less comfortable position, surrounded by questions that did not exist when data were less precise. These questions do not yet overturn the model, but they prepare the ground for more decisive observations that may either restore the simple constant picture with renewed confidence or point clearly toward a more complex form of dark energy. Dark energy enters cosmology as a constant because for a long time the data cannot clearly demand anything more complicated. The supernova evidence for acceleration can be matched well by a cosmological constant. The cosmic microwave background fits comfortably within that framework, and the large-scale distribution of galaxies follows the expected pattern. As surveys expand and instruments improve, however, researchers begin to ask in a more focused way whether dark energy might vary with time. To answer this, they need observations that trace the expansion history over a wide range of epochs with high precision. One of the central tools for this task is the systematic study of Type I, a supernova, the same kind of stellar explosions that first revealed acceleration. The basic principle remains the same. These events act as standard candles whose intrinsic brightness is well understood, so their apparent brightness and redshift together encode the distance scale and the expansion rate at the time their light was emitted. What changes in more recent work is scale and control. The Dark Energy Survey, an ambitious project using a wide-field camera on a telescope in Chile, is designed to collect a large, homogeneous sample of supernovae and galaxies over several observing seasons. Instead of assembling a small set of supernovae from different instruments and selection methods, the survey aims to build a single, internally consistent catalog with uniform calibration and carefully understood selection effects. Over its observing period, the Dark Energy Survey records the light curves of more than 1,000 Type I, a supernovae following their rise and fade in brightness and measuring their redshifts. This data set is one of the largest of its kind gathered by a single project. By itself, when analyzed within the standard framework, it appears broadly consistent with a constant dark energy component, though it allows room for small deviations. The real power comes when these supernova distances are combined with other measurements that probe different aspects of the universe. The cosmic microwave background provides constraints on conditions in the early universe and on the overall geometry and total energy content. Galaxy surveys map the distribution of matter and track the baryon acoustic oscillation scale, a preferred distance imprinted by sound waves in the hot primordial plasma. Weak gravitational lensing measurements add information about how structure has grown over time. When the Dark Energy Survey supernova sample is folded into this network of data and the combined results are interpreted through the lens of the lambda cold dark matter model, a more subtle pattern emerges. The combined fit seems to prefer models in which the effective influence of dark energy is not perfectly constant. To describe this in quantitative terms, cosmologists use a parameter known as the equation of state of dark energy, which relates its pressure to its energy density. For a true cosmological constant, this parameter takes a specific fixed value. If dark energy is a dynamic field or has more complex behavior, this parameter can differ from that value and may vary with time. In the Dark Energy Survey analyses, the best-fitting models sometimes correspond to an equation of state that drifts slightly away from the constant value at certain epochs, especially at intermediate redshifts, where the supernova data are particularly informative. The deviations are small, and the uncertainties remain large enough that a pure cosmological constant is still statistically allowed. However, the fact that multiple combinations of data gently lean toward evolution rather than strict constancy attracts attention. It is important to emphasize that these results do not constitute proof that dark energy is changing. Each component of the analysis has its own sources of uncertainty. Supernova distances depend on calibrations of brightness and on corrections for dust and host galaxy properties. Cosmic microwave background interpretations rely on assumptions about the contents and thermal history of the early universe. Baryon acoustic oscillation measurements must account for galaxy bias, redshift space distortions, and selection functions. Weak lensing requires careful control of shape measurement errors and atmospheric and instrumental effects. Correlations between data sets and modeling choices can influence the combined outcome. Nonetheless, even under cautious examination, the hint remains that a model in which dark energy has some mild time dependence can sometimes bring different data sets into slightly better overall agreement. For example, if dark energy were somewhat weaker in the relatively recent past and has grown closer to the constant value today, it could affect the inferred expansion rates and structure growth in ways that relieve some of the tensions described earlier. Alternatively, if its influence is gradually declining, that trend would also modify the detailed expansion history and might leave an imprint in the pattern of distances probed by supernovae and baryon acoustic oscillations. The current dark energy survey results cannot yet distinguish definitively between these possibilities, but they illustrate how sensitive the cosmological picture has become to the behavior of dark energy. The statistical language used to describe these hints reflects this sensitivity. Individual analyses sometimes quote confidence levels in terms of standard deviations, describing how strongly the data disfavor the simplest constant model compared with a slightly evolving one. In many cases, the evidence rises to the level that scientists call interesting but not conclusive. It is strong enough to justify further investigation and to motivate new observations, but not strong enough to declare that the long-standing assumption of a constant dark energy must be abandoned. This intermediate status is a familiar stage in the development of cosmological ideas. Past anomalies have appeared and faded as data improved or as previously unrecognized systematics were corrected. Others have grown more robust and eventually demanded new theoretical frameworks. In this context, the dark energy survey acts as an important test bed. It demonstrates that with large, carefully controlled samples, it is possible to probe the time dependence of dark energy in a serious way. It shows that the combination of independent probes can reveal subtle hints of evolution that would be invisible to any single data set. It also highlights the limits of current capabilities and the need for even more detailed maps of the cosmos. These needs shape the design of new instruments that push further both in depth and in coverage. To tell whether dark energy truly varies, astronomers require not only more supernovae, but also more precise measurements of the large-scale structure traced by galaxies and quasars across a substantial fraction of the observable universe. They need to measure how the baryon acoustic oscillation scale changes with time with higher accuracy, and to tie these measurements directly to the expansion rate at different epochs. This is where specialized spectroscopic instruments mounted on large telescopes and built to observe thousands of objects at once become central. By capturing the spectra of millions of galaxies and quasars, they can construct three-dimensional maps of the universe that encode its expansion history over billions of years. The first major results from these instruments arrive just as the community is grappling with the hints from the Dark Energy Survey, offering an independent way to test whether dark energy is constant or evolving. If these new maps confirm that the effective influence of dark energy has changed even by a modest amount over the last several billion years, then the assumption of a simple cosmological constant would have to be reconsidered. If they show no such change and instead bring the data sets into closer alignment under the constant model, then the earlier hints may eventually be traced to systematic effects. In either case, the process of testing dark energy with increasing precision reveals how much the fate of the universe depends on a component that is only now becoming accessible to detailed measurement, and how even small shifts in its behavior could alter the long-term story from a straightforward big freeze to something less settled. The dark energy spectroscopic instrument brings a new kind of precision to the study of cosmic expansion by shifting focus from isolated distance indicators to an enormous, detailed map of the matter distribution across much of the observable universe. Mounted on the Mayall telescope in Arizona, this instrument is designed to capture the spectra of thousands of galaxies at once. Each spectrum records how much the light from a galaxy is shifted toward redder wavelengths, which tells astronomers how quickly it is receding and how far its light has traveled through expanding space. By repeating this process night after night for years, targeting different patches of sky, The project builds up a three-dimensional map in which each galaxy is not just a point of light, but a marker with a measured position in both angle and distance. The goal is to trace the expansion history over most of the time since the first galaxies formed, using the large-scale pattern of their distribution as a kind of fossil record. A key feature in this pattern is known as the Baryon acoustic oscillation scale. In the early universe, before atoms formed, matter and radiation were tightly coupled and sound waves propagated through the hot plasma, compressing and rarefying it. When the universe cooled enough for electrons to join with nuclei and form neutral atoms, the radiation decoupled and the sound waves froze in place, leaving a preferred separation scale imprinted in the distribution of matter. Over billions of years, as matter collapsed under gravity into galaxies and clusters, this scale remained visible as a slight excess of galaxy pairs separated by a particular distance. By measuring how this characteristic separation appears at different redshifts, cosmologists can infer how the universe has expanded between those times and today. If dark energy is constant, the relationship between redshift and this preferred scale follows a specific curve. If dark energy evolves, the curve changes in a subtle but measurable way. The dark energy spectroscopic instrument is built to pursue this test. Its fiber system can observe light from thousands of galaxies in a single pointing, and its survey is planned to include tens of millions of galaxies and quasars spread over a large fraction of the sky. Early in its operation, the project releases a first major set of results based on its initial years of data, amounting to a map containing spectra for many millions of galaxies. When analysts examine this map and extract the baryon acoustic oscillation signal at different redshifts, they find that the measurements trace a detailed expansion history over a span of more than 10 billion years of cosmic time. On their own, these measurements already provide strong constraints on how the expansion rate has changed. When they are combined with other data such as the cosmic microwave background supernova distances and weak lensing observations, the picture becomes even sharper. As in the case of the dark energy survey, results the simplest model with a strictly constant dark energy component remains broadly compatible with the data. However, the best-fitting combinations often lie slightly away from that simple case. In some analyses, the preferred models correspond to a dark energy influence that was somewhat stronger in the earlier part of the period probed and has decreased modestly toward the present, implying that the effective push of dark energy has weakened over the last several billion years. One way to express this is to say that the acceleration is still present, but its strength may be declining. This is analogous to a situation in which a driver keeps a foot on the accelerator pedal, but gradually eases off so that the car continues to speed up but at a lower rate than before. In cosmological terms, the expansion continues to accelerate, but the rate of acceleration may be decreasing compared with what a constant dark energy model would predict. Translating this picture into quantitative statements involves careful statistical work. The three-dimensional map is not a simple static object. It carries uncertainty selection effects and complex correlations. Analysts must model the way galaxies trace the underlying matter account for known observational biases and propagate all these factors into their final constraints on the expansion history. They then compare the data to families of dark energy models, some with constant behavior and others with slowly changing equations of state. When the constant model is tested, it often falls just outside the very best-fitting region of parameter space, though usually still within the broader allowed range. When models with a mild time variation in dark energy are allowed, they can sometimes fit the combined data slightly better. In some combinations, the preference for an evolving component reaches the level that scientists consider strong evidence, though still short of the most stringent standard for discovery. As always, potential sources of systematic error must be examined. The mapping of millions of galaxies involves complex target selection algorithms and spectroscopic pipelines. The conversion from redshift to distance requires assumed cosmological parameters, which must be treated consistently in the analysis. Galactic foregrounds imperfections in photometric calibration and the finite volume of the survey all influence the measurements. To check the robustness of their findings, scientists perform numerous tests, varying analysis choices and data subsets. The recurring appearance of a slight preference for evolving dark energy across different methods and combinations strengthens interest in the possibility that the cosmological constant picture is incomplete, even if it does not yet compel a definitive conclusion. The implications are significant. If dark energy has weakened by even a small fraction over the last several billion years, the long-term trend may matter greatly. Should its influence continue to decline, the acceleration of the universe could eventually slow and perhaps stop. The expansion might then transition into a different regime, one in which matter again plays a more prominent role, or in which the sign of the effective pressure reverses, leading to deceleration or even future collapse. On the other hand, the apparent weakening might level off, leaving a residual constant component that still drives a big freeze, only with a somewhat altered timetable. There is also the possibility that the suggested trend is an artifact of subtle systematics not yet fully understood. The dark energy spectroscopic instrument is designed to continue observing for years, increasing the size and depth of its map and refining its measurements of the baryon acoustic oscillation scale. As the data set grows, statistical errors will shrink, and the ability to distinguish between constant and evolving dark energy scenarios will improve. At the same time, other projects are coming online that will provide complementary views of the cosmos. Space-based missions will measure weak lensing and galaxy clustering over vast areas of the sky, while ground-based observatories will discover enormous numbers of supernovae. Together, these efforts will test the hints emerging from the spectroscopic map with independent methods. For now, the first results from the Dark Energy Spectroscopic Instrument mark a turning point. For the first time, cosmologists can trace the expansion history over the bulk of cosmic time with a detailed three-dimensional map and ask whether the influence of dark energy has remained perfectly steady. The answer from these early data is that a perfectly constant influence is still allowed, but is no longer as secure as it once seemed. The dominant component of the universe may possess a history of its own, recorded in the subtle ripples of galaxy positions across billions of light years, and it is this possibility that pushes the field toward a deeper investigation of what dark energy really is and how it might change. In the standard picture with constant dark energy, the future of the universe unfolds along a fairly simple path. As expansion continues, the average density of matter drops because the same amount of material is spread over an ever-increasing volume. Radiation thins out even more quickly as its energy is stretched to longer wavelengths. Dark energy, by contrast, is assumed not to dilute as space expands. Its density remains the same per unit volume, so as the universe grows, dark energy becomes ever more dominant in the total energy budget. Eventually, its influence far outweighs that of matter and radiation. At that stage, the expansion does not merely continue. It accelerates in a nearly exponential fashion. Structures that are not gravitationally bound drift farther apart, and more of the observable universe slips beyond any given region's horizon. Over extremely long timescales, stars exhaust their fuel, and no new stars form from gas because the gas itself becomes too diffuse. Existing structures age and fade in a cosmos that keeps stretching. This is the Big Freeze scenario, a universe that does not end in a final event, but in a gradual decline of activity as temperature and density approach constant low values. When dark energy is treated as a perfect cosmological constant, this outcome is remarkably robust. Small changes in the amount of dark matter or ordinary matter alter details but do not change the basic fate. The long-term acceleration remains, and with it, the tendency toward isolation and cooling. The indications from the dark energy spectroscopic instrument and related surveys introduce a potential complication at this stage of the story. If dark energy is not exactly constant but has weakened slightly over the last several billion years, the projected future becomes more nuanced. The first question is whether the apparent weakening is real or a temporary fluctuation in the data that will disappear as measurements improve. Assuming for the sake of exploration that the trend is real, the next question concerns its long-term behavior. Does the effective strength of dark energy continue to decrease at a similar rate? Does it level off to a new constant value, or does it follow some more complex path? Each of these possibilities leads to a different class of cosmic futures. If dark energy settles into a new, slightly lower constant value, then the qualitative picture of a big freeze remains with some quantitative differences. The expansion would still accelerate forever, but the rate of acceleration and the timescales on which various processes occur would change. Structures might remain in causal contact for somewhat longer, and the dilution of matter and radiation could proceed at a slightly different pace. From the human perspective, these differences would be subtle, but from a cosmological perspective, they would indicate that dark energy has a history rather than being a timeless background. This alone would be a significant change in understanding, because it would point to an underlying degree of freedom in the dark sector that has evolved over cosmic time. If instead the influence of dark energy continues to decline gradually, then more dramatic alterations become possible. As its density falls, the balance between dark energy and matter shifts. In the standard model, once dark energy dominates, matter never regains control. In an evolving scenario, however, there could come a time when dark energy becomes comparable to, or even smaller than, the effective density of matter, especially if there are additional components such as massive neutrinos or other fields that contribute to the overall dynamics. Should dark energy tend towards zero, the universe would eventually transition from an accelerating to a more gently expanding or even coasting regime in which the expansion rate slowly decreases but never quite halts. In such a universe, the big freeze might still be the ultimate fate, but the path toward it would differ from the constant case, and some of the standard inferences about isolation and horizon structure would need to be revisited. The most striking possibility arises if dark energy not only decreases, but eventually becomes effectively negative in the sense that its pressure and energy density act to slow the expansion rather than accelerate it. In general relativity, a component with sufficiently negative energy density on large scales can counteract expansion, and if dominant, can cause the universe to decelerate strongly and eventually reverse its expansion. In this picture, a universe that is currently accelerating could, in the distant future, experience a slowdown, a halt, and then a contraction. As the contraction proceeds, structures that have drifted far apart would begin to move closer together. Background radiation would heat up as it is compressed. Over very long times, this could culminate in a state with high density and temperature, a kind of mirror image of the early hot phase, sometimes referred to as a big crunch. In such scenarios, the same component that once drove acceleration becomes the agent of collapse when its properties evolve through a critical threshold. The present hints of a modest weakening of dark energy do not by themselves imply that such a reversal will occur. The extrapolation from a slight change over a limited time interval to a complete sign reversal far in the future involves assumptions about how the underlying physics behaves. The point of considering these possibilities is to illustrate how sensitive the long-term fate of the universe is to the detailed time dependence of dark energy. A slow decline that never crosses zero would lead to one class of outcomes, while a decline that does cross zero would lead to another. There is also the conceptual mirror image of a weakening dark energy, a component that grows stronger with time. Some theoretical models of dynamical dark energy, often involving scalar fields slowly rolling down potentials, allow for behavior in which the effective equation of state dips below the value associated with a cosmological constant. In such cases, the energy density of dark energy can increase as the universe expands. If that trend persists, the acceleration itself can grow so rapidly that even gravitationally bound structures are eventually torn apart, in a scenario sometimes called a big rip. Galaxies, solar systems, and ultimately smaller bound systems would successively lose their cohesion as the expansion overwhelms local gravity. Current data, including those from the Dark Energy Spectroscopic Instrument and the Dark Energy Survey, do not favor such extreme behavior. If anything, the hints of evolution point toward a mild weakening rather than a strengthening of dark energy. The Big Rip remains an instructive theoretical counterpoint, showing that an evolving dark energy sector can, in principle, lead to very different fates. However, the weight of current observations suggests that if dark energy evolves, it does so gently. Between the relatively tame modification of a big freeze with slightly altered parameters and the dramatic reversal of a big crunch lie more subtle intermediate scenarios. In some models, dark energy behaves like a field oscillating around a minimum, leading to small periodic variations in its effective equation of state. These could modulate the expansion rate without radically altering the ultimate trend. In others, dark energy couples weakly to other components, leading to energy exchange between sectors that slightly changes the way matter and dark energy densities evolve. There are also models in which the apparent evolution of dark energy arises not from a true new field, but from modifications of general relativity on large scales where the geometry of spacetime responds differently to matter than in the standard theory. Each of these possibilities must be confronted with data. Many are already tightly constrained by the requirement that they not spoil the success of the standard model in explaining the cosmic microwave background and the large-scale structure. Those that remain viable typically involve small departures from the cosmological constant case consistent with the modest deviations suggested by current observations. From the perspective of cosmic fate, what matters is not whether dark energy evolves by a few percent over the last half of cosmic history, but whether those changes indicate a trend that continues and amplifies or one that stabilizes. Because astronomers can observe only a finite portion of the universe's timeline, directly they must infer the long-term behavior from patterns in the available data and from theoretical models grounded in fundamental physics. The emerging possibility from the first generation of precise dark energy surveys is that the universe may not be headed along the simple, unchanging trajectory once envisioned. Instead, the dominant component that shapes its expansion could itself have a history, and that history might still be unfolding. Whether it leads to a slightly adjusted big freeze, a delayed but still eternal acceleration, a future turnaround toward contraction, or some more complex sequence of phases, is not yet known. What is clear is that the assumption of a perfectly constant dark energy, once a convenient and plausible simplification, is now under observational scrutiny. And with it, the long-term forecasts built upon that assumption are becoming more provisional. In this sense, the work of mapping galaxies and measuring subtle ripples in their distribution is not only a technical exercise in precision cosmology. It is an attempt to determine whether the universe's distant future is already fixed or still subject to gradual change driven by the evolving properties of the vacuum itself. In the search for an explanation of dark energy that can accommodate possible evolution over time, cosmologists and theoretical physicists turn to a range of ideas that extend beyond the simple cosmological constant. One broad class of models treats dark energy as arising from a field that permeates space somewhat analogous to the fields already familiar from particle physics, but with very different properties. In these scenarios, often grouped under names such as quintessence or dynamical dark energy, the energy stored in the field and the way it rolls or moves through a potential landscape determine its effective pressure and energy density. As the field evolves, the equation of state of dark energy can change, leading to subtle shifts in the expansion history. These models can be tuned to behave very similarly to a cosmological constant over much of cosmic history, while still allowing mild variation that might account for the hints seen in current data. They offer the advantage of embedding dark energy in a framework that is conceptually similar to other known phenomena, such as the inflationary phase proposed for the very early universe, which is also driven by a field with unusual pressure. However, they also raise new questions. The mass scale associated with such a field would have to be extraordinarily small, and its interactions with ordinary matter would have to be suppressed to avoid conflicts with laboratory experiments and solar system tests of gravity. Building a theory in which such a field arises naturally without extreme fine-tuning is challenging, and this motivates ongoing work at the intersection of cosmology and high-energy physics. Another broad direction involves modifying the laws of gravity themselves on large scales. General relativity has passed stringent tests in many settings, from the precession of planetary orbits to the behavior of compact objects and the propagation of gravitational waves. These tests, however, mostly probe gravitational fields in regions that are relatively dense or over distances typical of stellar and galactic scales. It remains logically possible that gravity behaves slightly differently when averaged over cosmological distances. Modified gravity theories attempt to capture this possibility by altering the relationship between matter and the curvature of spacetime, or by introducing additional fields that mediate gravitational interactions. In such models, the apparent effect of dark energy might emerge not from a separate fluid or field, but from the way gravity responds to the contents of the universe. Some versions can mimic a cosmological constant at the level of the expansion history, while predicting different behavior for the growth of structure, offering a way to test them through comparisons of galaxy clustering and weak lensing data. Others naturally lead to evolving effective dark energy, where the deviation from general relativity becomes more or less pronounced over time. As with dynamical dark energy, these theories must thread a narrow path between fitting cosmological observations and satisfying local tests of gravity, and many candidate models have been constrained or ruled out by data. A third set of ideas involves topological features or defects in spacetime, such as hypothetical cosmic strings, domain walls, or textures. These are relics that might arise when fields in the early universe undergo phase transitions, leaving behind regions with different configurations. In some scenarios, networks of such defects can contribute to the overall energy density of the universe in a way that changes with time. While most simple defect models are tightly constrained by observations of the cosmic microwave background and large-scale structure, more complex possibilities remain under consideration, particularly in combination with other forms of dark energy or modified gravity. In all of these approaches, the guiding principle is the same: to connect the phenomenological description of dark energy defined by its effect on expansion with a more fundamental description rooted in fields, particles, or geometry. The hints from surveys such as the Dark Energy Survey and the Dark Energy Spectroscopic Instrument provide targets for these theories. If observations continue to suggest that the equation of state of dark energy differs slightly from that of a pure cosmological constant or evolves with time in a specific way, theorists can use that information to narrow down the space of viable models. Conversely, if certain classes of models predict features such as distinct signatures in the growth of structure or correlations between dark energy behavior and other observables, future surveys can look for those signatures. The interplay between theory and observation becomes particularly important because the energy scale associated with dark energy is extremely low compared with the scales probed in particle accelerators. This makes it unlikely that direct experimental confirmation of specific dark energy fields will come from laboratory experiments. Instead, the universe itself serves as the laboratory, and cosmic history becomes the experiment. Another line of reasoning connects dark energy to unresolved issues in quantum field theory, particularly the problem of vacuum energy. In quantum theory, even empty space is not truly empty. Fields exhibit fluctuations, and these fluctuations contribute to an effective energy density. Naive calculations of this vacuum energy using known fields produce values that are many orders of magnitude larger than the dark energy density inferred from cosmology. Reconciling this enormous discrepancy is one of the long-standing puzzles at the boundary of particle physics and cosmology. Some theorists hope that a better understanding of how vacuum energy gravitates, perhaps through new symmetries or mechanisms, will lead naturally to a small residual dark energy that might in principle vary slowly over time. So far, no universally accepted solution has emerged. Theories that attempt to address the vacuum energy problem often involve radical ideas, such as changes in how gravity couples to vacuum fluctuations, or the existence of multiple vacuum states with different energies potentially realized in different regions of a larger multiverse. While such ideas are difficult to test directly, they influence how cosmologists think about the plausibility of various dark energy scenarios. Against this background of diverse theoretical possibilities, the data act as a stringent filter. Many simple models of dynamical dark energy have already been pushed into narrow corners of parameter space by observations that demand behavior very close to a cosmological constant over much of cosmic history. Modified gravity theories that produce large deviations from general relativity on cosmological scales often predict changes in the growth of structure or in gravitational wave propagation that have not been seen. Defect models that contribute significantly to the energy budget tend to leave imprints in the cosmic microwave background that are not observed. Yet despite these constraints, room remains for more subtle departures from the simplest case. The current hints of evolving dark energy, if they persist and strengthen with future data, would push theorists to focus on models that produce small but non-zero time dependence in the dark sector compatible with all other observations. Such models might involve fields with very flat potentials, screening mechanisms that hide modifications of gravity in dense regions while allowing them to operate on large scales or intricate interactions between different components of the universe. The challenge is to construct theories that are not only mathematically consistent, but also stable, predictive, and testable. In this sense, the possibility that everything known about dark energy might be incomplete is not a sign of failure, but a sign that the universe is providing new constraints that any successful fundamental theory must satisfy. The emerging observational picture in which dark energy may be slightly weaker now than several billion years ago is still tentative, but it already shapes the landscape of viable theoretical ideas. It narrows the space of possibilities and encourages the development of models that can be falsified by upcoming surveys. The ultimate goal is not merely to fit a curve to the expansion history, but to understand what kind of entity or modification underlies that curve, how it fits into a broader framework of physics, and what it implies for the past and future evolution of the cosmos. As instruments map the universe with increasing fidelity, the region where theory and observation meet becomes more sharply defined, and within that region, the question of whether dark energy is truly constant or part of a richer evolving sector becomes one of the central problems in modern cosmology. Statistical evidence plays a central role in the way cosmology advances because the universe cannot be experimented on in the usual sense. Astronomers cannot rerun cosmic history with different parameters to see what happens. Instead, they must observe what nature has already provided and use probability to judge how well different models account for the data. In this context, a common language for describing evidence involves the concept of sigma, a measure derived from the standard deviation in statistics. When researchers say that a result is at 1 sigma, 2 sigma, or more, they are expressing how improbable it would be for the observed signal to arise purely from random fluctuations if the underlying model were correct. Roughly speaking, a 2 sigma deviation corresponds to a confidence level of about 95% that the signal is not merely a random accident, while 3 sigma corresponds to a stronger confidence and 5 sigma to the very high confidence typically demanded in particle physics before claiming a new discovery. In cosmology, with its complex data sets and potential for systematic errors, these thresholds are treated with caution. A result at 2 sigma is considered suggestive, one at 3 sigma interesting, and one at 4 sigma compelling enough to draw serious attention. Yet the history of science contains examples in which even very high sigma levels have later been traced to unrecognized errors. For evolving dark energy, the pattern of evidence across different surveys is beginning to take shape in this statistical language. When the dark energy spectroscopic instrument data are analyzed on their own, allowing for models in which dark energy can vary, they tend to favor scenarios where its influence changes slightly over time, compared with a strict cosmological constant. The statistical preference in those analyses often reaches a little above 2 sigma. This means that if dark energy were truly constant, there would be only a modest probability that the data would happen to align so well with a mildly evolving model by chance. When the spectroscopic results are combined with other probes, such as the cosmic microwave background, supernova distances, baryon acoustic oscillations from independent surveys, and weak lensing measurements, the effective preference for evolution can increase. Some combinations reach levels corresponding to 3 sigma, or even somewhat higher, approaching what might be called strong evidence in a statistical sense. However, the precise level depends on which data sets are included and how systematics are treated, and no single analysis yet achieves the 5 sigma standard that would generally be regarded as a decisive discovery. This intermediate regime is one of tension and opportunity. The numbers are large enough to make it unlikely that all of the preference arises from random noise, but they are not large enough to rule out the possibility that subtle systematics or modeling assumptions are responsible. For instance, small calibration shifts in photometry, slight mismodeling of galaxy bias, or overlooked correlations in large covariance matrices can all tilt results in ways that mimic physical effects. The complexity of modern cosmological analyses, which often involve many parameters and high-dimensional spaces, increases the risk that apparent signals might be enhanced by choices in data selection or prior assumptions, even when researchers aim to remain objective. Because of this, cosmologists are careful to distinguish between evidence that is intriguing and evidence that justifies rewriting textbooks. A well-known example from another domain helps to illustrate why such caution is essential. At one point, an experiment studying neutrinos sent from a particle accelerator to an underground detector reported that these particles appeared to arrive slightly earlier than they should if they were traveling at the speed of light. The deviation was small in absolute terms, but statistically significant, reaching a level even beyond 5 sigma. If taken at face value, it would have implied that neutrinos were exceeding the cosmic speed limit set by relativity, a result that would have required a profound revision of fundamental physics. The claim generated intense interest and scrutiny. Over time, further investigation revealed that the early arrival was not due to a new physical phenomenon, but to a subtle instrumental problem involving timing calibration and a faulty connection in the experiment's equipment. Once corrected, the apparent faster-than-light signal vanished. The episode serves as a reminder that even very high statistical confidence does not guarantee that all sources of systematic error have been identified and removed. In cosmology, where direct experimental control is even more limited, this lesson carries particular weight. The hints of evolving dark energy emerging from current surveys therefore occupy a careful place in scientific discourse. They are strong enough to motivate new observations and theoretical work, but they are framed as provisional subject to confirmation or revision as more data arrive and as analyses improve. The community responds by planning and executing a suite of future missions and surveys specifically designed to address these questions. In space, instruments such as the Euclid mission and the Nancy Grace Roman Space Telescope are being developed to map the geometry and growth of the universe with unprecedented accuracy. Euclid is expected to measure shapes and redshifts for vast numbers of galaxies, providing detailed weak lensing and clustering information across a large fraction of the sky. The Nancy Grace Roman Telescope is planned to conduct wide field surveys of supernovae galaxy clustering and micro-lensing events with careful control of systematics made possible by its stable space-based platform. On the ground, the Vera C. Rubin Observatory is being built to conduct an extensive imaging survey of the sky, repeatedly scanning large areas to discover and monitor transient events, including supernovae, and to map the distribution of galaxies over time. Together, these projects will extend the reach of current studies, offering multiple independent ways to test whether dark energy is truly constant. They will improve measurements of the equation of state parameters that describe dark energy's behavior, reduce statistical uncertainties, and crucially provide new avenues for controlling and cross-checking systematics. For example, combining lensing measurements from Euclid or the Roman telescope with galaxy clustering from Rubin's survey will allow detailed tests of how structure grows, which in turn can distinguish between evolving dark energy and modified gravity scenarios. At the same time, expanded supernova samples will refine the distance scale, and improved baryon acoustic oscillation measurements will sharpen the map of the expansion history. If the evolving dark energy hints are real, these missions should see them more clearly and consistently, pushing sigma levels higher and narrowing the range of viable models. If instead the hints are due to residual systematics, the expanded data sets and varied methods are likely to reveal inconsistencies that point back to more mundane explanations. Either outcome will represent progress. A confirmation of evolution would signal that the simple cosmological constant picture is incomplete and that the dominant component of the universe has dynamics that must be understood. A refutation would strengthen confidence in the standard model and clarify where early analyses were misled. The process by which these outcomes are reached illustrates how modern cosmology operates. It is not a single breakthrough that overturns a theory overnight, but a gradual accumulation of evidence measured in sigma and weighted by careful assessments of uncertainty that slowly shifts the balance of plausibility. In this landscape, the phrase that everything known about dark energy might be wrong does not mean that previous work is discarded. Rather, it means that the effective description of dark energy as a constant may be only an approximation valid over a certain range of times and scales, but missing subtler behavior that more precise observations now begin to reveal. The role of statistical confidence is to signal when those subtleties have become robust enough that they can no longer be safely ignored. At present, the universe appears to be offering such signals at a level that demands attention but still invites caution, keeping the story of dark energy poised between consolidation and revision. In the early decades of the 21st century, the study of dark energy stands at an unusual juncture. On one hand, there is a clear, coherent framework that describes many aspects of the universe with striking accuracy. The lambda cold dark matter model ties together the cosmic microwave background, the large-scale distribution of galaxies, the pattern of baryon acoustic oscillations, the brightness of distant supernovae, and the behavior of clusters under gravity. Within this framework, dark energy appears as a constant contribution to the energy content of the universe, a simple term in the equations that causes expansion to accelerate and drives the long-term forecast toward a big freeze. On the other hand, as measurements sharpen and surveys expand, small but persistent tensions and hints of evolution raise the possibility that this effective description is incomplete. Instruments such as the Dark Energy Survey and the Dark Energy Spectroscopic Instrument do not overturn the standard picture, but they nudge it, suggesting that the influence of dark energy may have changed slightly over the last several billion years. The fact that such a subtle effect can even be discussed highlights how far observational cosmology has progressed. The universe is vast, and the signals that dark energy leaves in the data are indirect, yet astronomers now routinely measure tiny deviations in galaxy clustering slight shifts, in distance scales and faint distortions in galaxy shapes to infer properties of the cosmic acceleration. These inferences are then combined with space-based measurements of the oldest light to construct a consistent timeline from the hot, dense early universe to the present epoch when dark energy dominates the energy budget. The emerging picture is one in which the current era is not just another step in a monotonic expansion, but a transitional phase where the relative contributions of matter and dark energy are comparable enough that small changes in either can have large qualitative effects on the past interpretation and future fate. In this sense, the universe today may be in a particularly informative stage, one that allows dark energy to be probed more directly than would be possible in a far future dominated almost entirely by a constant vacuum component, or in a distant past dominated almost entirely by radiation and matter. The recognition that there might be evolution in dark energy also reframes older questions. The coincidence that the densities of matter and dark energy are of the same order in the present epoch has long seemed puzzling if dark energy is a true constant. If it instead evolves slowly, this coincidence could be part of a larger pattern hinting at dynamics that naturally bring the dark energy density into a range similar to that of matter at certain times. Alternatively, the coincidence might remain unexplained even in evolving models, pointing to deeper principles or selection effects that are not yet understood. Either way, the possibility of time dependence adds structure to the problem. It suggests that dark energy has a history, and that the present moment is one chapter in that history, rather than the simple consequence of a fixed parameter. The data now being collected serve as a record of this chapter. The three-dimensional maps of galaxies from spectroscopic surveys, the deep imaging from wide-field cameras, the precise light curves of supernova, and the delicate patterns of weak lensing all encode information about how the universe has expanded and how structures have grown. Each new release of data allows cosmologists to redraw the timeline of cosmic acceleration with finer detail and to test whether the curve that best fits it truly corresponds to a constant dark energy component or to one that drifts. At the same time, the field remains aware of its own limitations. The history of cosmology includes episodes in which apparent anomalies faded with improved data or with better understanding of instrumentation. It also includes genuine surprises that forced revisions of long-held assumptions, such as the discovery of cosmic acceleration itself. The current hints of evolving dark energy could with time follow either path. They might solidify with future surveys, confirming that the equation of state of dark energy departs measurably from the value expected for a cosmological constant, and that this departure changes in a consistent way with redshift. Or they might diminish as new observations and refined analyses reveal overlooked systematics or statistical fluctuations that had temporarily mimicked evolution. In preparing for both possibilities, cosmologists design experiments that emphasize redundancy and cross-checking. Space-based missions will observe the same regions of sky as ground-based observatories, but with different instruments and different systematics. Supernova distances will be compared with independent standard rulers such as baryon acoustic oscillations. Weak lensing measurements will be cross-correlated with galaxy clustering to test models of structure growth. The aim is to construct a web of constraints so dense that any genuine signal of evolving dark energy will appear consistently across multiple probes, while any artifact will reveal itself through inconsistency. This approach reflects an underlying shift in the role that dark energy plays in cosmology. Initially, it was introduced as the simplest addition to restore agreement between theory and supernova data, a constant term in the equations. Over time, it has become the dominant component of the energy budget and the main driver of long-term cosmic evolution in the Standard Model. Now, as the data hint that this dominant component might itself be changing, dark energy becomes a central object of inquiry in its own right. Its properties, whether constant or evolving, connect to questions about the nature of the vacuum, the possible existence of new fields or forces, and the validity of general relativity on the largest scales. In this broader context, the possibility that everything known about dark energy might be incomplete is both a challenge and an opportunity. It is a challenge because so much of modern cosmology has been built around the assumption of a simple cosmological constant. If that assumption proves only approximately correct, much of the existing analysis will need to be revisited with more flexible models, and some of the neat interpretations of data will become more intricate. It is an opportunity because any confirmed deviation from a constant behavior would provide a rare clue about physics, beyond the current theories, a sign that the universe is offering new information about its most pervasive yet elusive component. The situation today is therefore one of controlled uncertainty. The lambda cold dark matter model continues to provide an excellent first-order description of the cosmos, capturing the main features of its evolution from the early hot phase to the present accelerated expansion. Within this model, the Big Freeze remains the default fate, a universe that expands forever under the steady influence of a constant dark energy. Yet around this central picture, observations are beginning to sketch possible refinements. Slight shifts in the inferred expansion history, modest differences in structure growth, and the combined implications of multiple surveys suggest that dark energy may not be entirely static. These indications are not yet decisive, but they are clear enough that they must be taken seriously. As future missions launch and new data flow, the story will become sharper. The universe will not change its past behavior, but humanity's reconstruction of that behavior will improve, perhaps revealing that the component called dark energy has slowly evolved, perhaps demonstrating that it has indeed remained constant within tight limits. In either outcome, the exercise will deepen understanding. If dark energy is constant, the universe's fate will appear more firmly fixed, and attention will turn to explaining why the constant has the value it does. If dark energy evolves, the universe's fate will depend on how that evolution proceeds, and the task will be to uncover the rules that govern it. For now, the available evidence places the cosmos in an interesting position. The acceleration of expansion is real. Dark energy dominates the current energy budget, and the broad outlines of the standard cosmological model remain intact. At the same time, there are signs that the dominant component may not be as simple as once imagined. Between the early universe, where dark energy was negligible, and a far future in which it may determine everything, lies the present era, where its subtle behavior can be measured and tested. It is in this intermediate time that instruments scan the sky, spectra accumulate, and maps of galaxies grow, all in an effort to determine whether the universe is following a fixed script toward a cold end, or whether its expansion is being written by a component whose properties continue to change. Until the evidence is decisive, the fate of the cosmos remains an open calculation, with dark energy as its most uncertain term. In the quiet of the present cosmos, dark energy remains both familiar and unknown. It appears in equations as a simple term that accelerates expansion, yet its origin is not identified with any confirmed field or particle. Observatories on Earth and in space continue to gather light that has crossed vast distances and times, encoding the influence of this component in small shifts of wavelength in the clustering of galaxies and in the slight shearing of distant shapes. Each new survey refines the timeline of expansion, drawing a more detailed curve that traces how the universe has stretched from the early hot phase to the current era dominated by an invisible influence. In this continuously updated picture, dark energy is no longer just a placeholder for ignorance. It is treated as a measurable part of reality, with properties that can be constrained and perhaps eventually mapped. Its density and pressure are inferred, its behavior over time is tested, and its role in the future of the cosmos is examined with increasing care. At the same time, the core questions remain open. Is dark energy truly constant, a fixed feature of spacetime, or does it drift slowly as the universe ages? If it evolves, does it settle toward a stable value, fade away, or move toward behavior that changes the sign of its influence? The answers to these questions will decide whether acceleration continues indefinitely toward a cold, diffuse future, stalls into a gentler expansion, or one day reverses into contraction. For now, the data permit more than one path. The universe's recent history suggests that dark energy dominates and that expansion accelerates, but the subtle shifts seen in the most precise maps hint that this dominance may not be entirely featureless. Between the clear record of the past and the projections into the distant future lies a zone of uncertainty that observations are only beginning to penetrate. In that zone, dark energy sits as an unresolved term in the equation of cosmic fate, shaping everything while revealing only part of its nature, inviting continued observation and analysis as the universe carries its own history forward.